The Saturday Morning Physics. This week we're going to be going over a few different things. We're going to look at how we make particles in our accelerators, and we're also going to talk about how we detect those particles. I think the tour today, we're not going to have a tour. We're actually going to have a panel with us who have agreed to come in on a Saturday and talk to you and answer your questions about what it's like to be a physicist. You have some. Now some on your behalf. Anything else? Logistics. People on the Zoom, please put whatever you want to ask in the chat. If you feel like your questions aren't being answered, also put stuff in the pigeonhole. Anything else? I think the bathrooms are working this weekend, so hooray. With that, I think we should introduce the speaker. This is Cindy Joe. You guys know Cindy. Cindy is one of the co-chairs of Saturday Morning Physics, and she'll be moving into one of the leadership roles next year. Engineering physicist. College. Did you go for a master's? I can't remember.
Bachelor's in physics.
So Cindy has been around the lab for a long time, and one of the main reasons that me, as a neutrino physicist, can actually get. With that being said, we have our regular tradition. I got to stand up again. People on the Zoom, let's stand up.
How this works.
Gonna get ready to learn. Again, this is 3 big breaths. The first one. Let it out. Whew. The stress.
Stress.
Yeah. The next one. You should be in a good mood too. Doesn't push you in a good mood. Puts me in a good mood.
Always puts me in a good mood.
And then the last one. Out. Whenever you're ready.
Thanks, Brian. Thanks, everyone. Let me grab the clicker. Test my clicking abilities. And if not, it's right here. It's fine. Great. All right, we're going to get started. Thanks, everyone. I will say that there's a lot of information to get through that I have. And then also we actually have 2 speakers today. We'll introduce the second one in a bit. So we're spending the time on 2 separate talks. You're getting 2 talks for the price of 1 today. So I have quite a lot of information planned for today. And so I think I'm going to ask you, we always encourage questions, but I think I'm going to ask you to just kind of do urgent clarifying questions and just sort of more general things like how to, sort of questions that I can answer later. I will plan on doing so. We're at certain times throughout the talk, but it's going to be a lot of information very quickly. So I'm going to try to keep it quick. So I am going to close some things. You guys. Right, let's get started. So I titled my talk Introduction to Accelerators, but I was thinking maybe a good alternative title could be this. So the previous speakers have given us some pretty amazing talks on getting you excited and setting up how and why we do what we do. So Evan, the next speaker, and I have focused our talks on more practical aspects of what we do, how we do it, how it actually gets done. So hopefully we can share a little bit of that with you today. So you already heard a little bit of that from Brian's intro. Thank you very much, Brian. I just wanted to add to that, so I grew up in a small town in Arkansas. My parents are immigrants. I'm a first-generation college student. And, you know, I'm not going to belabor that. We can talk more about that later if you have any questions. But the thing that I wanted to get across is that we all have unique things about us that are challenges or are strengths that we bring to the table. And a lot of our challenges actually end up being our strengths, whether that's you're also a first-generation college student, whether you have a difficult family situation, whether there's some sort of, you have neurodiversity, something that is a challenge or is something that you have to continue to work around to do what you do. I just want to like validate those circumstances and say that I feel like those sorts of things are worth mentioning. Those things are part of what you bring to the table. No matter what you have going on, you're not alone. Your challenges matter. But so do your strengths. And so you guys bring something to the table that your perspective, your contributions, they matter in this field or any other field that you might go into. So I would say that, as Brian mentioned, I went to Reed College in Portland, Oregon. One of the notable things about Reed College, in addition to being a great school for physics, is they have a nuclear research reactor. I was a licensed senior nuclear reactor operator. That is me above Reed's 250 kilowatt research reactor. It really looks like that. It is this beautiful blue glow, which Evan will explain a little bit more. It's called Shrinkov radiation. And I have been at Fermilab since, feel free to ask me about nuclear reactor operations. I've been at Fermilab since 2010. For the first 7 years, I was a particle accelerator operator. And as you can tell from the nuclear reactors and the particle accelerator, I just like big science machines. I am currently an engineering physicist. Basically, how I explain that job is that I'm a problem solver. Whatever comes up, I come up with a solution to make it happen. So currently, I work with neutrino experiments, and I also manage the NUMMI underground. This is our facility. It's 350 feet underground, and the liquid argon test facility experimental areas at Fermilab. So I would say that much of my job involves living in the in-between spaces, between, for instance, the accelerator and lab operations people and the experiment people, and connecting to each other, helping them communicate and carry out their common goals. That's me in an accelerator tunnel on the top. That is in the main injector, which I think you saw a tour of before, and engineering physicists often wear hard hats. Also want to caveat, this is my take on the topic. I'm going to focus on my experience, but there are all sorts of other ways to talk about this. I encourage you to explore them, and I'll give more resources at the end. The main thing that I want to get across, so you know, some of this may be things that you're familiar with, some of this may be things that you're seeing for the first time. Either is great. The main thing that I want to get across is not like memorizing the equations or anything like that, but an explorational mindset and a way of looking at problems and working to solve those problems. So the mindset is what I want to get across, the way of approaching the world. So let's set up the motivation for this talk. First of all, what is a particle accelerator? What are we talking about with that? So when we talk about particles, we're talking about subatomic particles of matter. For instance, protons, neutrons, which are very cute. An accelerator is something that makes something go faster. So if you accelerate a car, making something go faster gives it extra energy. So a car that is speeding has more energy than a car that is parked, for instance. So a particle accelerator, put it together, takes particles of matter and adds extra energy to them. They are energy-adding machines. Typically, you'll hear me refer not just to one single particle at a time, but a whole collection of particles and how that aggregate behaves on average. It's a pretty good analogy to a beam of light, where you have a lot of particles sort of traveling as a whole. And it can also be refracted, focused, bunched, and otherwise manipulated. It really does work a lot like light. You'll hear accelerator people talking about beam optics. And I wish I could get into all the amazing things you could do with a particle accelerator, but for the purposes of this talk, I'm going to concentrate on what we do at Fermilab, which is high energy physics. However, they can be used for all sorts of other things. They are the tools of high energy physics. They are your microscopes. They are your telescopes. They allow you to see something about the particle that you could never see any other way. Furthermore, the de Broglie relationship on the right, which involves Planck's constant, and then also wavelengths and momentum. the de Broglie relationship tells you that wavelength and momentum are connected to each other in an inverse kind of way. So since Planck's constant is a constant, you can see that they're inversely correlated. So if you want to see really, really small things, for instance, if your lambda, your wavelength, you want that to be really, really small, you need your momentum on the bottom to be really, really large. And so that's why using particle accelerators to get us to really high momenta lets us see exciting, tiny things. Another exciting thing about accelerators is they allow us to go back in time. I'm going to put some caveats and some asterisks on that situation. They don't really let us go back in time the exciting way, in terms of like, I can come back to yesterday and have more time to get ready for this talk. But instead, what they allow us to do is to recreate conditions like those very, very long ago in the past. So like those just after the Big Bang, when the laws of physics of the universe were literally different. Things were denser, hotter, tighter, closer together. They just behaved differently. And that can give us more information, recreating those early conditions, which don't exist in the universe as we know it in any other way, or at least not that we can see easily, might give us more information about the formation of the universe, the structure of matter, where the universe might be headed. And also, since we have an energy adding machine, and Einstein's most famous equation told us that energy and mass are the same thing, and we can go back and forth. If we have one, we can get the other. E equals mc squared. Particle accelerator giving you extra energy means that you can create new particles out of that energy. New particles that never existed before. Maybe you start with boring old protons. Well, protons are exciting, but normal protons, and get new particles that you did not start out with and that do exciting extra things. Fermilab has quite a few particle accelerators. You've talked about some of them on the tour. I just want to like blow you away with how many we have and how exciting they are. And we also have a lot of experiments, and they have a symbiotic relationship to each other. These are just some examples of the neutrino experiments which I work with. The thing about accelerators is we have designed them to help us explore what we need to learn. You don't have to have particle accelerators to do experimental particle physics. For instance, just in the field that Brian and I work in neutrinos, you have IceCube, which studies high energy cosmic neutrinos with no accelerator involved at all. Diabay is another example of an accelerator of a neutrino experiment that just uses neutrinos coming from a nuclear reactor, like the one that I used to work with. But accelerators really give us a degree of control which is otherwise impossible, right? So you can control the type of particle, the energy, the flux, the direction. You can turn it on and off and like know that it's on or off without like turning off the nuclear power to an entire country or anything like that. So accelerators, because they give us that amount of control, they play a really important role in the experimental confirmation of our standard model and exploration of physics beyond the standard model. They do come with practical limitations, but there's also a great deal of engineering, of interesting physics, technology, and exploration of physics behind it. So you guys, I can't remember if you have already met Leah, our lab director. If you have not, you will meet her at the graduation. She is an accelerator physicist. And you know, I want to return to again and again, as I said, that accelerators are the tools used in particle physics, but they're also interesting sources of physics all in of themselves. So I don't want to say that accelerators just sort of play second fiddle. They are interesting sources of physics in and of themselves. And again, returning to that operational mindset. Everything, you know, the idea of, I keep wanting to come back to the idea of practical experience, adapting and designing your surroundings to obtain the result that you want. So everything we work with on a daily basis was designed by somebody in response to a problem they were experiencing. So, you know, I think that that's an exciting aspect of scientific inquiry, and it's an important part of the operational work that characterizes what my coworkers and I do. So we've gotten started. It's time to build a particle accelerator. So if we were to do that today, how would we start? First of all, when you start with a particle accelerator, it's very important to give it a great name. So I've decided that since it's my particle accelerator, it's the Synthetron. You can name yours after yourself. That's fine too. We're going to start with a name, and we're going to start with a piece of beam pipe, just sort of planning out where we want our particles to go. How do we start with the accelerating part? Well, I know that several speakers have already talked about the fundamental forces of matter, the fundamental forces of nature. And I just want to back up a little bit and talk a little bit about Newton's second law. So I also want to make sure we're all on the same page with notation. So remember that a vector is a quantity that has both a magnitude or size and a direction associated with it. And by convention, there's all sorts of different ways, but by convention in my talk, I've put little arrows that point to the right. So when you see a little arrow above something, that is a vector. Reminder about Newton's second law, force is equal to mass times acceleration. And whenever you see an equation, it's important to listen to what that equation is trying to tell you. So in this case, the force is proportional to both mass and acceleration. So you can see that if we add extra mass, you're going to get a greater force. If you add extra acceleration, you're going to get a greater force. Another concept is work. Work is force over a distance. That little triangle is lambda, the Greek letter, is delta, the Greek letter, and that is for change in. So a change in position, a change in x is an integral part of the work being done. So force acts over a distance. The position of something is changed, and you get work out of that. Work takes energy. So if I have an object and I move it around with the energy of my body, that is needed. Work takes energy. Energy is conserved. So potential energy can be changed to kinetic energy. So if, for instance, this object that I have in my hand, this roll of tape, if I raise it, I'm doing further from the floor, I am doing work against the force of gravity. I can then, I'm creating more potential energy. If I drop it, then it's going to get accelerated towards the floor, and that potential energy I've created is changed into kinetic energy or energy of motion. And then I'm creating potential energy again by exchanging potential energy by raising it up again. So what I just demonstrated in front of you is a way to use gravity to accelerate a massive object. So if we were designing our accelerator, could we use gravity to do the accelerating part? So if we just kind of turned our beam pipe on its end and dropped particles the way that I was dropping that piece of tape. So here at Fermilab, our RFQ injection LINAC, the very beginning of our LINAC, pictured to the right, accelerates hydrogen ions, H- ions, to 750 kiloelectron volts of energy. I'll explain all of those units and things later. Could we design a gravity accelerator that does the same thing? And if so, what height would we need to drop our particles from? So we go back to our work equation and say, oh yeah, force over a change in distance. We set our parameters given the ones we just had, acceleration due to the Earth's gravity, solve for our height. You guys don't need to do this. I will plug it all in for you, make some substitutions, plug in the masses of things, the energy of things, and get to a solution of a height of an extremely large number. So that's saying that if we were to do that, just kind of back of the envelope calculation, as physicists say, this is not the way that, we kind of made some assumptions there. But if we made those assumptions, we would have to drop this hydrogen ion from 73 million kilometers away, which is it's about half the distance between the Earth and the Sun, to get that equivalent acceleration, over 45 million miles. That is a lot of miles. That is a lot of work. So while I'm not going to say that it wouldn't work, I would say that if this was my machine, and luckily it is, I would rather not use the method of just dropping things and using gravity to do our acceleration. So let's try something else. So, I kept saying that we're going to return to this practical aspect. We're going to return to this operational aspect. I will say that gravity can be used to accelerate particles. It's not that it doesn't actually work. So for instance, cosmic rays, which we study in physics quite a bit, are particles that are entering the Earth's atmosphere accelerated from outer space over huge distances by gravitational effects. We actually do a lot of physics using gravitationally accelerated particles. The gravity accelerator does work, but again, for the kind of results we want to see on the time scales and distances we want to see them, other methods may be more practical. Again, engineering, like much of life, is a series of careful compromises. So you have trade-offs, and that you just try to make those trade-offs cleverly to maximize the results that you want. If we want to do things on sort of like a human scale, don't want to make millions of years for us to get the information we want. We don't want to like kind of like luckily have things happen. We might want to think further about how we further engineer the things that we want. So let's go back to our forces and say, what if we went to a different force? What if we went to the electromagnetic force, for instance? Seems like another good choice. So let's talk about how those forces work. So a field is this mysterious thing in physics. It's pretty confusing, but I like to think of it as basically a way to explain the ability of an object to affect another object without sort of directly touching that object. Some examples of things that use fields to interact are electric fields, magnetic fields, gravitational fields. Those things might not necessarily be in contact, but they are affecting each other. So how an electric field is produced is a charged particle is involved. So you have a charged particle, it creates an electric field sort of radiating out from it, and another charged particle might see that field from the first particle and experience a force. Just like you probably learned in school, like charges tend to repel each other and opposite charges tend to attract each other. So here's the equation of the force resulting from an electric field. So Q is our electric charge, the quantity of our electric charge. E is the magnitude of the electric field involved, and F is the force that is resulting from that electric field. So remember that if a particle experiences a force over a distance, we can say that work was done. So the gain in potential energy, or the acceleration and the gain in kinetic energy. I mentioned a unit called an EV earlier. That is the amount of energy that you gain by accelerating 1 electron worth of charge over 1 volt worth of electric potential. It's an incredibly small unit for the most part. So typically in accelerator land, and particle physics land, we'll talk about those using metric prefixes. So kilo, mega, giga, or tera for 10 to the 3rd, 6th, 9th, and 12th power. Usually, so intuitively, I find this a little bit hard to think about. So I try to draw an analogy between electric potential and the sort of more humanly intuitive gravitational potential. So if you kind of, think about having this ball held up and you drop it and it accelerated, you raise it with potential energy, you can think of electrical potential energy and kinetic energy as doing the same thing, just in a slightly different way. Again, it's changing that particle from rest to motion and back. So if we set up an electrical potential, would that accelerate a particle? Answer is yes. Some electrostatic accelerators work just like that. If, for instance, you've gone to a science museum and had your hair stand on end, a Van de Graaff generator is a type of electrostatic accelerator. I'll also talk about a few more here. An early one, a very early type of particle accelerator, dating back to 1870, is the cathode ray tube, or is originally called the Crookes tube. That's a way to accelerate particles using just domains that we said. And this technology is still used in many applications today. And the Cockcroft-Walton, which was our first accelerator at Fermilab, or first accelerator in the sort of chain of events that happens at Fermilab for many, many years. So this was discovered in the late 20s, early 30s by people named Cockcroft and Walton, invented, I should say, rather than discovered. And it was used for over 40 years as our original proton source. You might remember seeing this from the virtual tour or the in-person tour that you went on last week. It's a really smart design that allows really high voltages and therefore really high accelerations to be produced. And again, all those beautiful smooth edges are to reduce the chances of charge building up and causing a spark. And those sparks are just as important as what's going on, because you're trying to engineer what you want to happen and trying to engineer away what you don't want to have happen. So those sparks, that eventual breakdown of your ability to hold an electric voltage, is an important limiting factor in the work that you want to do. So as you push the envelope, at some point, you actually can't hold that high level of charge anymore. you kind of reach the breakdown voltage of the ceramic resistors or whatever is involved, and that charge tends to bleed off through sparking. So, you know, you can build higher and higher voltage accelerators to get to higher and higher energies, but at some point you can't do that anymore physically, engineeringly. So how do we approach this? Is instead of making higher and higher and higher voltages, at some point we run out of our ability to go to higher and higher voltages. What if we try making smaller voltages? That's no problem, but just having a whole lot of them. So lots of small pushes instead of one giant push. So now we get to the next part of particle accelerator, the RF cavity. That is how we accelerate and manipulate particles when it comes to your modern particle accelerator. RF stands for radio frequency, which is the band of the energy used in the electromagnetic spectrum. It's kind of in the megahertz range. Now we get to our next type of particle accelerator, which again uses RF cavities in a very clever way. So this is used again at the beginning stages of Fermilab's LINAC, or linear accelerator, and at Fermilab it accelerates H- ions up to 400 mega electron volts for them. Again, an RF cavity is a metallic structure in which an oscillating electric field is produced and controlled. So remember that that force that we just talked about due to an electric field, when the particle encounters an electric field, it experiences that force. I'm just going to call it a push. That push gives it a little bit of extra energy and accelerates it. But I just made a big deal about how RF cavities use oscillating electric fields. So they go up and they go down, they go forward and they go backwards. And that oscillation is great. That's how our electric system works. But it's not super helpful if you want to go forward and then forward without going backwards, right? So what about the part of the field that points in the direction opposite from the direction you want to go, the wrong direction? That's where the really clever design and engineering of this type of RF cavity comes along. So you have a series of accelerating gaps and followed by a series of drift tubes. So you have accelerating gap where the acceleration happens, drift tube where nothing happens except the particle is shielded from the part of the field that we do not want it to experience. The drift tubes block out the undesirable part of the field. So here in, let me see if I can get this. Here in the positive direction part of the electric field, our beam of particles is going through this RF cavity, this accelerating gap, at just the right time to experience this positive part of the electric field. And by the time the electric field oscillates and goes to the negatively pointing part, the beam has actually moved out of this and into the drift tube, where, yes, the electric field back here in the accelerating gap is pointed the wrong direction, but the beam doesn't know and doesn't care because it's already over here. And then by the time it's continuing to drift and coast and travel forward, by the time it gets here, you've designed it so that it is just the right time to experience that forward push again. So forward push, backwards push, but we only see the forwards pushes, and that is how this all works. So here's an actual picture of the inside of our RF cavities at Fermilab. You can see it's this beautiful, shiny copper thing. And what you're seeing here is these, the things that you see sort of hanging from the top are the drift tubes, and then the spaces in between are the accelerating gaps. So here you kind of see a side view in which here's the drift tube, hides the field, here's the accelerating gap, sees the field, hides the field, sees the field. And you see that these are actually getting longer and longer as you go in this direction, because as your particle gains energy, each time it crosses a gap, it gains more energy. It starts going faster and faster. So in the same length of time, it goes a longer distance. And then it gets another push, and it goes a longer distance, and it gets another push and goes a longer distance. Those drift tubes, and therefore the RF cavities, are going to get longer and longer and longer. All right, so we figured out a way to accelerate our particles. So if we take our beam pipe and we slap a bunch of RF cavities onto it, we now have an accelerator. So like Nobel Prize is just around the corner for us. But the thing is about the Nobel Prize is they don't just give it out for normal things. They give it out for extraordinary things. So if we really want to sit super high energies, probe those tiny, tiny particles, and make incredibly exciting discoveries, we have to hit the highest energies that we possibly can. So let's think about how we want to do that. So our linear accelerators, I'm going to give an example at the Stanford Linear Accelerator Facility at SLAC. In the past, they had an accelerator which accelerated electrons up to 50 GeV, 50 giga electron volts, and it took 2 miles. That's the longest one that we've built so far. Just as comparison, the Large Hadron Collider in Europe, which gets energy up to at least, I think at this point it's higher, 13 TeV, tera electron volts. So if, you know, these are not equivalent, they're different particles, they're different ways of working, but if you were to just kind of draw a rough comparison, we would need 260 entire SLACs, or about 520 miles to get up to that 13 TeV. I looked up a city that was about that distance away from Chicago, and I got like Rochester, New York. So we would need to build, naively, a continuous machine that was here all the way from Chicago, like straight through Canada into Rochester, New York. So, and that would be like nothing but beam pipes and RF cavities and vacuum chambers. So again, going back to things that we practically can or cannot do, probably the Canadians wouldn't like that. I think the Americans wouldn't like it either. So it's a little impractical, and we maybe want to go back to the drawing board for that. All right, so that's a little bit tricky. So what do we try? Let's try some other way. So if instead of having just like, oh, you get to higher and higher energies by making it longer and adding more RF cavities, what if we made it into a loop? So you can maybe sort of recycle the same RF cavity and like go in a smaller distance. So a charged particle, the way that that bends is using a magnetic field. So what if we put that whole thing inside a magnet? So first, a little bit about magnets. Oh yeah, and a quick thing about notation. So if I draw where my arrow or where my vector is going, things that are in the plane of the page are pretty easy. You can draw up and down or whatever. By convention, something that goes in the direction into the page or the screen is going to look like a circle with an X on the end, and something that's coming out at you is going to look like a circle with a dot in the middle. And you can kind of remember that intuitively if you think about like an archery arrow and whether you're looking at the pointy end or the feather end. So if it's like pointing at you, you're kind of seeing the tip, and if it's pointing away from you, you're seeing the end. So back to magnetic fields and forces, if moving charged particles, also known as electric currents, produce magnetic fields. And that's how electromagnets work. So those fields, again, interact with other moving charged particles and exert forces on those. So magnets are what we do to how we actually bend and focus particle beams. And the equation, which I'm going to give you associated with that, has a name, it's the Lorentz force equation. And that has, again, now we have 2 vectors on the right side and 1 vector on the left. So that force comes out of 3 quantities. We've got the charge. I think we've got the Q is still the magnitude of the charge, but the V is the direction the particle is traveling. That's the velocity. The B is the direction the magnetic field points, which is going to be some different direction. And F is the direction of the force exerted by the magnetic field on the particle. So this is the first time. The other equations that I showed you had a vector on the left and a vector on the right. So those vectors are pointed in the same direction. F equals ma or F equals QE. The force is the same direction as the acceleration or the electric field. In this case, I've got 2 different vectors on the right side. So what direction does my force on the left point in? And that's where the right-hand rule comes in. Some of you may have experienced this before. This the direction of the resulting force is actually perpendicular to both the direction that the particle is moving in and the direction of the magnetic field. So remember that a vector has both a magnitude and a direction. The magnitude part is easy, just multiply the size of the v and the q and the b, and you get a number for the force. But to get the direction for the force, that is where the right-hand rule comes in. By convention, there are two directions that are perpendicular to both the velocity and the field, and we have chosen one of them using the right-hand rule. So I am going to demonstrate this. So I'm going to turn my back to you guys, so I'm facing the same direction as all of you. To get the direction of the force, you're going to, whatever direction this is, point out your fingers in the direction that the particle is moving, and then figure out which direction the magnetic field is. Whatever direction that is, you're going to curl your fingers in whatever direction that is. So you might have to bend your wrist, you might have to turn it around, and then you just stick out your thumb, and that's pointing in the direction that the resulting field is. So that was confusing, so I'm going to give you an example, but I'm just preparing you for what we have going on. So we're going to try this again. Actually, we're going to try it again in a moment, but I have a couple more caveats. F is the force exerted by magnetic field, remember, on a charged particle. So it changes direction depending on the sign of the charge. It could be this direction or it could be that direction. The right-hand rule is going to give you the direction for positively charged particles, that is protons. To go to a negatively charged particle, I recommend that you use the right-hand rule and then take it the other way. So the same magnetic field is going to bend positively charged particles like protons one direction and electrons the other direction, which is kind of exciting. We use that for many different things. So let's try this out. I'm sorry, the people on Zoom, it's a little bit harder for you to see me up here, but I'll try to make my movements very expansive because I know the camera's way up there. So let's try this out all together. So suppose that we have a positively charged particle traveling up in this diagram, right? So the positively charged particle is traveling up this way, that way, and it enters a magnetic field that is pointing forward, into the page of the screen. So which of these drawings, A, B, C, or D, is going to represent the path the particle will take after entering the magnetic field? Please try this out very quickly. I know that we also need to move along a little faster. And remember that F equals QV cross B. So take out your right hand and start, kind of trying this out. So remember, the particle is traveling up, and the V is traveling up, and the B field is traveling into the screen. And I get some people in the audience, once you've thought about this, to call out something that you think, and maybe some people on Zoom can type in what they think, A, B, C, or D. Kind of keep this pretty quick. Anybody have a possibly just call out? B, I heard B. You guys agree with them? Does somebody else have a different one? Somebody on Zoom said D. All right, let's try this. Let's see. The answer is B. Congratulations. So we're going to try, and it doesn't matter if you said B or you said anything, said D or you said anything else. Let's go over this together. So again, I'm sorry, people on Zoom. I'll try to make my emotions very expansive. So the direction the charged particle is traveling is up. So I'm going to take my right hand and I'm going to move it in an upward direction. Now remember that the direction that the magnetic field I said was pointing into the page. So I'm going to take my right hand and I have to point it this way because, well, I mean, my fingers only really bend one way. So I'm going to rotate my wrist until my fingers are able to point forward into the page. So that's telling me that my resulting field, again, for a positively charged particle, is pointing to the left. So I have a force that's pointing to the left. However, remember my particle is already traveling up. So my particle is now traveling up and to the left, which is how we get B. So it's not traveling to the right, but it's also not just kind of like moving steadily to the left, because we still have that forward motion. So it's traveling both up and to the left, and that makes it bend. That's how we get this gentle curve. And again, remember that this is all perpendicular to the direction of motion. So it doesn't make your particle move, slow down, or get faster. It only changes its direction. We're going to move right along. I'm sorry that I'm not going to take time for questions today because I want to be able to show you a demonstration and make it a little bit difficult for me. But I'll be able to show those of you in person this a little bit later, but it's very exciting. We have this beam tube. I've got a camera pointed on it. I will show you on the slides what you are seeing here. So there we have a cylinder of hydrogen gas. It has electrons boiling off of a filament. The electrons are your charged particles. The hydrogen gas is just around to make the path of the electrons visible, since it'll fluoresce whenever they run into each other. We've got something to accelerate the beam, and then the whole thing is mounted inside a magnetic field created by these Helmholtz coils. The setup looks a bit like this, just for those of you on Zoom or those of you who can't see it very closely. It is indeed covered by a box right now. And then we're going to make the room as dark as possible. Hold on just a bit. Let me. Control. So this is the view from the webcam that's inside here. Laura, would you mind darkening the lights? So it's a little bit hard to see here. But can you guys, it's a little bit hard to see here. Let me. All right. So you can kind of barely see, I think. It's a little bit more visible, but do you guys see there's kind of a gentle circle, a gentle, slightly blue curve that's trapped? A little more visible now. Okay, I think we're starting to see it a little bit. You guys see that? All right, so that is the electrons that we're seeing from the live view. I'm going to go back to the I'm going to go back to our slides. It's kind of like a cooking show where what you're seeing is, here's one I prepared earlier. Here's a picture that I made earlier of the setup. So let's see what's going on here. So because of the fluorescence, we see the path of the electrons. It's glowing blue here. So an electron coming off the filament is being accelerated in the upward direction. Uniform magnetic field from the Helmholtz coils is coming out of the page towards you. Remember, F equals QV cross B. So our field is traveling, our particles are traveling up. Remember, our field is traveling towards you, so I'm going to rotate my wrist so that my fingers bend in this direction. So you'd think that the force would go to the right, but remember, it's a negatively charged particle, electrons. So that's why that force bends to the left. So that's why we're getting this bend that's in this direction as opposed to that direction. Yes, please. Thank you, Laura. So what if I go to my power supply? It's right down here, and I adjust the dial for the accelerating voltage. What do you guys think might happen? Can I get some people in the room to call out a possibility? Yes, please just say it. Maybe the ring will get bigger. Any other ideas? I think that's a great suggestion. Yeah, other ideas? You guys agree with that possibility? Well, let's try it real quick. Mind making the room darker, Laura? Thank you. I'm going to try turning the knob right down here on this power supply live and see what happens. A little hard to see, but do you guys see it? It does actually seem to be getting bigger. Do you see that? The radius is getting a little larger. I'm going to return it back to what it used to be. Awesome. So very well done. We take it back to our slides here. Yes. So again, here's the one that I did earlier. The radius of the circle does get larger. So I think of this intuitively as kind of like the particles are traveling so fast, so energetically, that they can only be bent a little bit by the magnet power. So that leads us to our next type of accelerator, the cyclotron. So this design comes out of the understanding that charged particles react to an electric field by accelerating, getting a little bit extra energy, going a little bit faster, and then they react to a magnetic field by changing their direction. So in the cyclotron, you have this split RF cavity. These are called Ds because it kind of looks like a big capital letter D, and in between is the accelerating gap where the acceleration happens. And then the whole thing is inside a uniform magnetic field, which is perpendicular to the direction with the particles travel. So what you're seeing on the top picture is sort of a, that is just sort of flattened and then inserted into this sort of magnet, sort of like a sandwich, so that the magnetic field is pointing in the up and down direction, and the particles are sort of traveling in this plane that's in between. So think of this a little bit like a drift tube balloon, but it's stretched out and it's curled around. So let me see. So if we start out here in the middle, remember your charged particle is going to experience a curve in an electric field, and then it hits this accelerating gap. It gets a little push, gets a little more energy. And remember, whenever you get a little bit of acceleration, a little bit more velocity, it's going to trace out a larger circle. So now it comes around and it's in a different place than it was before. Gets another push and it's going to trace out an even bigger circle, another push, even bigger circle. And so that's why we get this characteristic spiral pattern. As the particle accelerates every time it comes across the gap, the radius of curvature gets larger and larger. And so you can see that by the time we get to the outside, we've hit this gap so many times that we're traveling at pretty high energy. And this is a very exciting type of accelerator that's still used today for many, many types of purposes. Often medical accelerators tend to be cyclotrons. First one was invented by Ernest Lawrence. It fit in the palm of a large hand. Ernest Lawrence actually got a Nobel Prize and an element named after him, which I think is pretty much winning when it comes to a scientist. And as we continue to push the envelope, remember, we're always trying to push the envelope. We get bigger and bigger and bigger cyclotrons with bigger and bigger magnets. This is an example of the Lawrence Berkeley cyclotron magnet, which is 60 inches in diameter. One of the people sitting up there on the top is Robert Wilson, the founding director of Fermilab, and this building that those of you who are here in person are in right now is named after Robert Wilson. We push the envelope more and more, and we get to the largest cyclotron that we've ever made, which is at Triumph facility in Canada. You can see all these people sitting there. It has the largest beam radius of 310 inches, which is almost 26 feet. So, okay, remember, we're pushing the envelope, build bigger and bigger cyclotrons, but you gotta kind of figure out that, wait, I mean, there is a limit to how big you can make a cyclotron. So how do we overcome those limitations? Remember, we have this huge magnet that's just like producing a uniform magnetic field over the whole thing. So if we could use smaller magnets, maybe reuse the same magnet so we didn't have to make like one big one that was the entire room, it would be great if we could do that. In fact, it would be great if no matter what energy you're at, your particles are just going to travel in one loop instead of a spiral that gets bigger and bigger and bigger. So let's think about how to do that. And you guys might already have some ideas on where this is going. So I just changed the accelerating voltage knob. I did not do anything to the velocity knob. So if we increase the velocity if we increase the magnetic field, and let me back up and say this again. Earlier, I changed the velocity. I did not change the magnetic field. What if we kept the velocity the same and did change the magnetic field? Make our magnetic field bigger. What do people on Zoom think? Can somebody tell me? Anybody on Zoom, what do you think will happen if we did that in front of everybody right now? Laura or Brian, could you tell me how Zoom is doing?
Zoom says it would be a smaller radius.
They think smaller radius. I think people on Zoom are very smart. And let's try this out. Would you mind making it a little bit darker, Laura? We're going to try this again. I'm going to crank over this knob here. I know you guys can barely see this, I'm sorry. I'm going to try to make it, you see that it's getting smaller? You guys see that? Awesome. Very good. That was me cranking the knob a little higher so that we had more magnetic field. Very, very good. We're going to go back to the slides. Thank you, Laura. Again, whenever I did this earlier, that is exactly what we got. The radius of the circle got smaller. So we've just done two important things, right? So if we increase the velocity, which makes the radius bigger, and we increase the magnetic field, which makes the radius smaller at the same time, like if I turn those two knobs very, very carefully in a balanced way, we could get a radius that stays the same. So we've just figured out a way to make the circle bigger and make a circle smaller, and we can use that instead of one giant magnet. We can have a ring that is giant and has many smaller magnets inside of it. And that is how the synchrotron was invented. So if we time and phase everything just right, we can up the current of the magnets to keep the beam bending at just the right angle to go around and get another acceleration at the RF cavities, and we up the magnetic field again and again. At higher and higher energies, we can go, and this will all work out. It's really exciting. That's part of the reason why the highest energy machines in the world are all synchrotrons. It's clear they'll probably continue to be, and they can be absolutely huge. So the Fermilab's main ring and then Tevatron was about 4 miles around. The LHC at CERN is, I think it's about, yes, it's about 17 miles around. It's even on this diagram. They can, I mean, it's big enough that it kind of travel, you know, it crosses the border of and, you know, these are theoretical for now, but like, what if we keep extending that? I went to a particle accelerator conference and somebody was proposing this like giant accelerator floating in the Gulf of Mexico. So it would like kind of like take up that entire place and sort of touch base at the edges of the Gulf. Fermi himself apparently maybe doodled this on a cocktail napkin or something, but he just sort of like was throwing out this idea, what if we make an accelerator that goes around the entire Earth? So really exciting stuff. I mean, that sounds pretty awesome to me. I'm an engineering physicist. I solve problems. So this kind of thing gets me really excited, but sadly, we don't have infinite amounts of money. And even for a normal accelerator, there's all sorts of practical concerns. So for instance, what about all that high-powered stuff? Requires high power. All of the high-powered stuff gets hot. It needs to be cooled, so we have maybe cooling water. We have to keep good vacuum so that our particles don't like run into stuff and scatter. So there's all sorts of things that you need to think about. Instrumentation. This is a wire chamber, which is a type of instrumentation that we use. Evan will talk a little bit more about other types of ways to detect particles. And practical concerns are really important. Again, there's the operator coming out in me. Things are not necessarily going to be perfectly the way that you designed. Maybe there's a problem with one of your RF cavities and the beam just doesn't get like the perfect right kick. Or maybe there's like a water leak, or maybe your vacuum is not completely perfect. You need to be able to respond to any and all of those problems and be able to do the science anyway. You have to come out of the theoretical design world and into the imperfect real world and figure out how to solve those problems. And I also want to point out, I presented these particle accelerators kind of one after the other, and it might be tempting to feel like, oh, well, synchrotrons are clearly better than LINACs or cyclotrons. It's not really like that. You choose the right machine for the right purpose. All of these machines have their own uses. They're all actually still used. And you want to choose the right machine for the right situation. The last few minutes, I'm sorry that we started a little bit late. Again, you guys got to go on a tour, which I appreciate. You guys can look at me talk about more on this if you go on YouTube and find my Physics Slam presentation. But I just want to talk a little bit about what makes a good particle accelerator operator. So your typical Fermilab operator, like I was in the day, had just a physics bachelor's or something related to that. Not necessarily a higher degree. It does sometimes happen. It is a rare job that you can only get in physics using only a bachelor's. But more important than the thing that you study, it's the kind of person you are and how you approach the world. So, you know, having that sort of mindset, a curiosity, a drive to learn, a tinkering mindset where you want to tease out all the details of a particular problem, the tenacity to pursue that problem until it is solved. And I think this third point is super important, the ability to put your own ego aside about how smart you are or are not, and ask stupid questions and learn from every opportunity and every person. So again, things don't always work out in real life the way that they might on paper. You have to get your hands and maybe your whole body dirty. You can plan things out, but the beam is going to do what the beam is going to do, and you have to adjust your expectations and respond to what you actually experience. So again, the main control room, which I think some of you got to see in person and some of you got to see virtually, and some pictures of accelerator operators in the field. These are all colleagues of mine. On the left is a colleague going out in a blizzard on his snowshoes to go fix something that was in the field. Here are some more colleagues working on cleaning up a water leak. And on the right is my facility that's 350 feet underground, also very exciting. Again, a few thoughts to go forward about, I remember I said I wanted to get across a mindset and not just a list of equations. I think that part of being a good and ethical and happy and productive scientist is being a good and ethical and happy and productive person. So I got into physics not because I was necessarily good at physics. I actually didn't do very well in my first class in physics in high school. It was a challenge, but that was a good thing as far as I was concerned. Not that I wasn't doing well. Of course I wanted to do well, but it was a challenge, and I didn't want to let that challenge beat me. So even though I wasn't doing well at first, I kept working at it until I got better and better, and I kept taking classes and eventually ended up. So I just want to tell you that, like, you guys are more than your grades and your test scores. It is really important to ask those to be the kind of person that you want to be around. It's a really important thing, and we'll talk more about this probably later with our panel, but the people that you want to work with are not necessarily the ones who have the answer to all the problems just in their head, but the people that are just fun and interesting to work with. Again, you know, be ready to learn something from every situation, every person. Ask stupid questions, because that means that it's more important to you to learn the thing than to look as if you already know the thing. Be brave. Do the things that you want to do, and which might be hard, but which you know to be the right thing. And it's so important as a scientist in any kind of community, as a student, as a member of society, to act with integrity and do the things that you know to be right. Again, you know, you guys know this stuff. You know, but I just want to like remind you again. I think that in physics and anything else, it's important not just to be good at school or good at physics, but to be good at like life and working with people, and that includes including yourself as people, applying all sorts of intelligence, including emotional intelligence, to make the world a better place. Again, I think you guys knew this, but I want to remind you and just say it out loud. That is the end of this. You guys can contact me if you need more information. Again, thanks for building that accelerator with me. Hopefully we can get a Nobel Prize together, and more information for you to explore. Thank you very much.
I'm not going to do much of an introduction except for say Evan. I've worked with Evan as well. He was a postdoc here while I was a postdoc. More or less taught me how to do some of the things that I'm doing now. So whenever you're ready.
All right. Thanks, Brian. It's good to be here again talking to all of you, both in person and on Zoom. Yeah, so Cindy just gave you a great talk on how we make these particle accelerators, and then I'm going to tell you how we then take advantage of these accelerated particles and build experiments to observe them. There's lots of different types of detectors, so I'm only going to kind of give you just the tip of the iceberg today. I know we're a little short on time. We might not have time for all the questions you might have. Do feel free to reach out to me. I'm always happy to talk after this presentation is over. I want to start by addressing, what kinds of things are we trying to do in particle physics, right? What are we trying to study? So we could be trying to discover new particles. This could be both things that we know should be there, that theory has predicted should be there, that we haven't observed yet. So recently, this was observing the Higgs boson. This could be, dark matter, dark energy searches. This could also be things that are the unknown unknowns, right? The things that we don't know aren't there. We could also then be trying to make precision measurements of particles and their properties, right? More precisely measuring how they interact, rates, really probing this, the standard model of physics and that framework, looking for, any, numbers that are slightly off from these predictions, right, or other symmetry violations. We could be, as Cindy talked about, also probing, the origin or early state of the universe in some of these experiments, such as why there's more matter than antimatter. And so to go about doing that, we're basically using the scientific method. We're going to make observations and ask questions, conduct our experiment, and then, draw a report off of that. So let's start by thinking about a couple of the questions that have been asked recently. I think these have been touched on or will be touched on in some of the other lectures in the series. So a couple examples, right, is what is the mass of the Higgs boson? Or what is the rate of electron and muon neutrinos observed coming from the atmosphere? So if you go to a theorist, they're going to draw you a couple pictures, right? And a theorist would say, well, if you're looking for the Higgs boson, you could have two gluons that fuse together. They produce this virtual Higgs, and then there's going to be a decay, and you should see two photons in a final state. So easy, right? Just go look for this picture. In the case of neutrinos, you could say, well, you have a muon neutrino that's coming in. It exchanges a W boson via the weak nuclear force with a neutron, and then you go look for a muon and a proton in your detector. Okay? So then we have to start building an experiment to see those things, right? So there's things that we can directly see in our detector. So in the case of this neutrino interaction, we can directly observe, the tracks that the muon and the proton are making in our experiment. And then we have to infer from the way we've built the experiment and the analysis that this neutrino or Bayer was here and made these tracks, which we can't see directly in our experiment. So then we start, designing these detectors. And so you always start by asking, what's the the primary physics goal of my experiment, right? What's the one measurement that I'm trying to make? Maybe it's measuring the mass of the Higgs boson. And then you ask, what other measurements could I also make with the same detector? Or if I change my design a little bit, what other science could I do? Because of course, if I'm building this large experiment with a lot of people, the more different questions I can answer with the same experiment, the more efficient that is, right? It's a more efficient use of time and money. It gets more scientists interested in joining your experiment to maybe answer the question that they're interested in that your detector can also help them answer. And so then you try to figure out, well, what is the event I'm interested in, my signal, for example, those two photons from Higgs boson decay, and what other events in my detector, the background, what are things that might look like that, but aren't the interaction I'm interested in? What is this background? How frequently do they occur? And how can I construct my experiment to separate those two? So I'm getting the events I'm interested in, and I can throw away these background events that I don't care about. And then there might be other constraints in your detector, right? How large am I having to build this? Am I building an experiment to run for a couple weeks, a couple months, or does this have to run and not break for a decade? Am I putting this underground? Is it going to be an accelerator, or am I putting it in space or in the ocean? What kind of data rates am I taking in the experiment, right? How many computer disks am I filling up with the data? How do I store it? How do I process it? Does my detector have other special requirements, right? Does the materials have to be radiation hard because of the environment they're in, like an accelerator? Are they at ultra cold cryogenic temperatures? Am I doing, picosecond timing of these electronics? What are all these special requirements? And so you spend, years, planning these experiments, working with experts to try to maximize the physics potential of your experiment, answer the question you're interested in, at some reasonable cost and scope. So as you go about this design process, it's quite often that you're going to identify, a detector design or technology that doesn't exist yet, or it exists, but it hasn't been used the way that you're trying to use it. So before you then build this giant experiment and spend millions of dollars, you want to have some idea that the technologies you're using are going to work the way you intend them to. And so at Fermilab and other labs around the world, we have what are called test beam facilities. We also here have an irradiation facility. This is where I work, is at these facilities on site. And so experimenters will bring prototypes. They'll bring small pieces of their experiment, electronics, and they'll put them in a beam of known particles and known energy, where for a few days, a few weeks, they can test these components and make sure they're functioning the way they're supposed to. They can put them in a radiation field and see, do they survive, right? How damaged do they get after this radiation? And just make sure that each component of their experiment meets the design specifications before they build their large detector. This is usually part of review processes of the design phase. And this R&D test beam campaign can take years in some cases of experiments. This can be multi-year, 5 years plus of just designing and optimizing these components for the experiment you then build. So then you actually build the experiment, which can come in all different shapes and sizes. These are a few examples of some different things. So this here at Fermilab is the G-2 experiment. So there's this large magnet here that was measuring certain properties of a muon here at Fermilab. This is one of the NOVA detectors here at Fermilab, which Brian and I both work on. This is measuring properties of a neutrino using a liquid scintillator-based detector. This is another neutrino experiment, IceCube, where they've drilled into the ice at the South Pole and have a very large detector in the ice. Super Kamiokande, you see, is this giant tub of water, which we'll talk about later. Protodoom, this is the inside of a cryostat that's filled with liquid argon looking for neutrino properties. This is looking at the inner layers of the CMS detector at CERN, which is doing Higgs boson physics. They can come in other sizes, right? So Crayfizz is the example of an experiment that was using just a network of cell phone cameras to do cosmic ray physics, with a network of cameras around the world. There are medical imaging applications, of course. LIGO is an example of a very large laser interferometer that was studying properties of gravitational waves. And so then you take these experiments, and for an example of CMS and super Kamiokande, you have this nice diagram of what Higgs boson interaction should be, and then this is a picture of what one of these interactions actually looks like inside the CMS detector. And this is the example of a neutrino interaction inside this large tank of water at super Kamiokande. And we're going to come back at the end of the talk after we've talked about detector properties and then really explain what each of these images mean and how they're telling us that these are the interactions that took place inside of them. And so then we take that data and we turn it into reports that we then publish out into the world. I'm going to focus the rest of the talk, though, then on just this experimental phase, right? How are we designing and performing an experiment? We can detect particles from all different sources, but for the remainder of this talk, I'm really just going to focus on these artificially produced sources of particles coming from the accelerators, and particularly the accelerator complex, often here at Fermilab. So there's kind of two basic geometries that you can construct your experiment with when you're talking about particle accelerators, right? You can have these fixed target designs, and so you have your beam of particles from your accelerator. It's smashing into some target material. It's producing other particles coming out of it, and that's where you then arrange your detectors. You might have a magnetic field, you might have various tracking chambers, maybe a calorimeter measures energy. You kind of build it in layers coming from this interaction, right? One example of this is like the Dune neutrino experiment, right? We're producing a beam of neutrinos here at Fermilab. We're going to send it 800 miles through the Earth to South Dakota, where we have a series of detectors along the way. But ultimately, this is just a fixed target experiment. It's just stretched out over a lot of distance. The other design that you'll see is this collider design. So in the case of, like at CERN, the LHC, they have two streams of protons, right? So they're being accelerated in opposite directions, and they collide into each other. And so in that type of design, you then want to build your detector in layers, radiating outward, right? So instead of having this linear construction of detectors, you basically fold it around the beam pipe because the particles are going to be coming, spherically, right? They're coming in all different directions, and so you need to wrap your detector in layers, to take advantage of that and study them. So then what are we looking for in our detectors, right? This, you've heard your talk on the standard model, so this can include, both kind of the usual suspects, right? We have our fundamental quarks, we have our leptons, we have the protons, neutrons, pions, other particles that are built from these, our standard set of forces. We could also be looking for then more exotic things, right? Dark matter, supersymmetric particles, sterile neutrinos, magnetic monopoles, some of these, more exotic theories. So now we have to, in our experiment, how do you tell that what you saw was an electron and not a muon or a proton or so on, right? So we have a number of different ways that we can distinguish one particle from another, right? Each particle has a unique set of numbers that define them, right? They're going to have different masses, charge, spin. We can look at the conservation of energy, right, of the interaction to kind of reconstruct what did we see, conservation of momentum. We can also look at charge parity and time, both conservation and violation, to try to tell, reconstruct when we see this image in our detector, what happened to get that. Different particles are also going to have different lifetimes. They're going to decay at different lengths, and so we can take advantage of all of these properties. So we have a number of different tools we can use to detect particles. I'm going to go through kind of a few of these, and then build some detectors based on that. Right. So first up, realize I think in the room here we're not seeing move the bar to the other side. We can talk about ionization. Right. So ionization is the process of removing or adding an electron to an atom. Right. You're making it positively or negatively charged. So if you have a particle that's passing through some material. It's depositing energy into that material, and so it can deposit energy that knocks an electron, off of the material, right? So then you've produced, these both positive and negative ions as this particle is traveling through the space. Right? Each material is going to have different properties, right? You can have gases, liquids, plastics, crystals that can all produce ionization. They might have different properties about how they're doing that. So then if we add an electric field to this material, that's going to separate the ions, right? The electrons are going to drift one way, the positive ions are going to drift the other way. And so then if we set up some, device, a pad to collect those electrons, we then get, an electric current, and we can measure that. So you could construct a series of these pads, and then basically you're measuring the track, right? You're collecting ionization as a particle is traveling through a detector. So you build up an idea of where did that particle go. You also could get timing information then from when did energy get deposited on each of these detectors, and then how much ionization you collect. Tells you, how much energy was deposited in the material, right? That then produced these ions. So you can get a lot of information from ionization. Another, similar process is that of scintillation light. So again, as you have a particle traveling through a material, it can produce photons. Those photons can be absorbed in this material. It gets excited. And then when it de-excites, it's then emitting more light, right? So you can, again, have different materials that are producing the scintillation light, liquids, solids, gases. You can have both organic and inorganic scintillating materials. The light they're producing is going to be at a very specific wavelength, right? That's going to be characteristic of that material. It's going to absorb energy, and then it's going to de-excite, and different materials are going to have different properties of the light they're producing. That informs then how you build your detectors to see that light. And so then we have devices to collect the light. There's photomultiplier tubes, photodiodes, that then takes that light, counts the number of photons, and converts that to an electric signal. You can get the same information on energy tracking and timing from, again, building a series of these detectors to collect that light at different points. So one example of a light collection device then is a photomultiplier tube that is quite common in particle physics, right? So here you have a photon that's coming into the device. It's hitting some photocathode material that's then going to knock off electrons via the photoelectric effect. These electrons are going to be accelerated, through a series of stages, right? So you're going to increase the voltage as it goes, and as these electrons are accelerated and hit these diodes along the way, they're going to cascade. They're going to produce more and more electrons, and so that's where you get this multiplication, where you might have one photon coming in and get gains of about 10 to the 6 in your signal coming out of the other end. So you get some electric signal. These tubes can operate at a variety of temperatures. Sometimes you need them cryogenic, sometimes not, and they might have other operating characteristics to study these materials, right? So one thing that's important is, where are these photomultiplier tubes efficient at measuring the wavelengths, right? I said that the materials that are producing the scintillation light are producing that at all different wavelengths. So here is a plot of the wavelength of the light, and this is the quantum efficiency. So this is how efficient is a material at converting a photon of that wavelength into an electron. And so there's different materials. These are the materials that would make up that window, that front of the photomultiplier tube. And you see that for different materials that I can choose, they have different quantum efficiencies at different wavelengths. And so, for example, if I know that the wavelengths I'm interested in are way out in the infrared, I wouldn't pick a material that has no sensitivity to that wavelength. So it all depends on matching the material in your experiment and what wavelength is it producing to the right detector to see that light. Another example of a light collection device is an avalanche photodiode. So here you have basically a silicon wafer. So you have a strip of silicon in most cases. You've done things to that silicon to give it regions where there's, an enrichment of an electrons and a depletion layer as well. So you've constructed this in layers and also applied a voltage so that, again, when a photon is coming in, it's entering an absorption region where it's going to kick off an electron that then gets accelerated through a multiplication region where you then, again, produce this shower of signal that you then collect. These typically have quite high quantum efficiencies and lower operating voltage, where you might be talking about tens or hundreds of volts rather than thousands of volts in a typical photomultiplier tube. They're also then typically lower gain. These can be very sensitive to being at just the right operating voltage to get these effects to occur. You might lower temperatures here to reduce the noise in backgrounds. These tend to be smaller in size, right? So you might need a lot of them to get the same coverage as a phototube. Taking this concept then one level further, there's something called a silicon photomultiplier. So here you're taking something like your photodiode that you saw on the previous page, and you're operating at a voltage, it's called Geiger mode, where if you have one photon coming in, you're getting an avalanche of electrons coming out. So you're getting very high gains of about 10 to the 6. But because you're getting this very high burst, this avalanche breakdown, you can't tell the difference between if you had two photons coming in at the same time or one photon, because it's going to produce the same avalanche. So these tend to operate as a series of microcells, right? They're very small in size. You're often maybe operating them in low light regimes where you're only getting one photon at a time in a particular cell. But because of this granularity and this very high signal, you can then essentially just count the number of photons you're seeing in your device, right? So here's a plot that's showing you 0 photons, 1, 2, 3, 4, 5, and so on. So you get this very crisp light collection image, again, in certain regimes. So I want to talk through how we choose the light collection devices for one particular experiment. So this is a picture of NOVA, which I've done a lot of work on. NOVA is a neutrino experiment here at Fermilab. So it's a very large plastic detector. And so it has basically these PVC tubes of plastic. They alternate vertical and horizontal orientation, so you kind of have this honeycomb structure. Each of these plastic cells is filled with mineral oil, which is the scintillating material. So as a particle passes through, it deposits energy and produces scintillation light in this mineral oil. That light is collected by an optical fiber that runs up and down each cell. And then that fiber is connected to a pixel on an avalanche photodiode, which converts that light to an electric signal. So as a particle passes through, you know which of these cells the particle passed through because you see signal in them, and then you know how much energy was deposited in that cell. So again, this is a plot that's showing you, again, the wavelength of the light that's emitted and the quantum efficiency. So the scintillating material in NOVA is producing light here that's in the blue regime, right? It's somewhere between 400 and 450 nanometers. So you kind of have this blue light coming out of the liquid scintillator. When the optical fiber captures that light and re-emits it, it shifts that light into the kind of the green spectrum, right? Between 500-ish and 600 nanometers. You also notice that the exact wavelength of light depends on the distance the light had to travel in that fiber, right? Because the fiber's a loop, if a particle is right at the top of the cell, it only has to travel a short distance and might have one wavelength that it's producing. And if it's at the bottom of the cell, it's traveled a different distance, and that's affected the wavelength of the light that you're seeing. And so we could put a photomultiplier tube at the end of the cell, but you see that a photomultiplier tube, especially at the wavelengths we're interested in, has a pretty low quantum efficiency. Whereas the avalanche photodiode, again, especially up in this 500 to 600 nanometer range, is much better performing, right? So we get, 8 to 10 times more light that we're collecting by picking the photodiode in this application over the phototube. Again, this really depends on the specific goals of your experiment. There's plenty of applications where you would want the photomultiplier tube and not the photodiode. It all depends on the choices. But in NOVA, you would be completely missing some particles at the bottom of your detector just because you wouldn't be efficiently seeing the light that is being produced. So we can take these detectors, both for ionization and scintillation, and we can use them to track particles. So this is a picture of the inside of the CMS detector, and these are millions of silicon pixels, these photodiodes that are in the inner layers here near the beam pipe. And this is an example of ice cube. And so this is down at the South Pole, and they've basically drilled strings of photomultiplier tubes, kind of like Christmas lights, down into the ice here. So they've instrumented a cubic kilometer of ice, and they're looking at neutrinos coming from extragalactic sources. And so these are extremely high energy. And so in CMS, you need a detector that is very dense, right? You have millions of sensors in a very small space to separate out the different tracks. In IceCube, you have your detectors are separated by, I think it's like 17 meters in between each tube, because you don't need that density to see a particle of that energy. And so a goal in all of these experiments, right, is you want the best tracking resolution that's required to make your physics measurement, but you want to minimize dead material because that degrades energy resolution. And of course, to build more channels, it costs more money. And also, you're producing more data that you then have to analyze. It affects the processing rates, and so that's an optimization problem. That more phototubes doesn't necessarily mean it's better, depending on the goals of your experiment. So we can also use magnetic fields, just like Cindy talked about, right, to distinguish particles. So as you learned in the last hour, right, charged particles are going to bend in a magnetic field. You can also understand their momentum from that curvature, right? So you can look at a curved particle in your magnetic field, and you can reconstruct its momentum. You can also separate a charged particle from its antiparticle. They're going to bend in opposite directions, and you can use that to distinguish them. Of course, this only applies to charged particles. So if you have photons, neutrons, neutrinos, they're just going to pass through this field, undeflected. You're not going to be able to do those measurements in the magnetic field. Then we come to calorimetry, right? So we're measuring the energy that a particle loses while it's passing through our detector. So of course, to fully measure a particle's energy, you have to be able to stop it, right? If the particle passes through your detector and it wasn't stopped, then it's carrying some energy away with it, that's missing. And so when you're then looking at the picture of what happened in my experiment, there's some piece of that puzzle that you don't fully understand. And so you want to be able to range out and stop as many particles as you can. Of course, you're going to do this using different materials, right, which have different properties, because different particles are going to stop differently, right? If you have electromagnetic particles, things like electrons, muons, that are mostly depositing photons that are mostly depositing their energy electromagnetically, that's going to look differently than your hadronic interactions, which are mostly interacting via the strong nuclear force. And so you might construct your detector in layers, right? You have a tracking chamber, and then you have your electromagnetic calorimeter. You're going to stop your electrons and photons, collect that energy, and then you may have something denser. You're now trying to get your hadrons to interact, and then you're ranging out the muons, because if you put maybe your muon chamber first, something really dense, then everything else just travels a short distance. You don't get the information that you're looking for out of it. So these showers, the way the particles interact, these showers evolve differently over time, right? So in a hadronic shower that's governed by the strong nuclear interaction, right? You have some hadron that's coming in, it then interacts with your material, produces other hadrons, maybe some pions, might be an electromagnetic component as well, and this kind of evolves over time. In the electromagnetic case, right, so here we're looking at both an electron and a photon. They're interacting electromagnetically. So an electron comes along, scatters, it produces, Bremsstrahlung radiation. It produces a photon. That photon then may pair produce, and so it's going to produce an electron and positron pair. And this kind of cascading shower develops as you pass through the detector. You notice that there's a difference between the start of the electron shower, which is a charged particle that's going to start depositing energy, and that of a photon, which is going to pass through some amount of material, invisibly before it then pair produces and has these two electrons. And so depending on how you've constructed your detector, you might be able to take advantage even of this small but perhaps noticeable difference in the beginning shape of these showers to tell, did I see an electron or did I see a photon in my detector? You can kind of build these calorimeters then in two different types, right? You can have a sampling calorimeter. So I might have an alternating series of material that I've put there to try to get the particle to interact, and then something, like a scintillating material to then sample that energy and collect that. And so you're kind of getting this evolution of the shower shape, but you also have put some dead material in here, right? So you're losing some energy, and you can calibrate and try to estimate that, but you are losing some energy in this dead material. You can also have these homogeneous calorimeters, right, where I just have this slug of scintillating material. I have a PMT at the end, so my electron can come in here. It can deposit all its energy, and I can look at that light. But then I don't have any image of how the shape of that shower looked, right? I just see there was this much energy here, but I don't know more than that necessarily. So Cherenkov radiation is another concept that's used a lot in particle physics, right? So you're probably familiar with this from sound first, right? That planes can travel faster than the speed of sound under certain conditions, and they're producing this shock wave behind them. The same is true for light, right? You can have a particle that's traveling faster than the speed of light for a certain material, not traveling faster than the speed of light in a vacuum, but for a given material, it can travel faster than the speed of light. So when doing so, it's going to produce this cone of light behind it. Cindy showed you this image of what that looks like inside a nuclear reactor, that blue glow from the Cherenkov radiation. So you get this cone of light because these light waves have coherently interfered, right? And you have this amplification effect. What this light looks like is going to depend on the particle traveling faster than the speed of light in that material. So it depends on the index of refraction of the material. It depends on the velocity of the particle. That's gonna then play together to produce light of a particular angle, this cone, so that you can then use that to do particle identification inside your detector, right? You can measure the angle of the light that you're seeing. You can look at the momentum of the particle, and then you get the separation then of what pions and kaons and protons look like, because they're producing these different angles in your detector medium. Now again, you do see that there's a thresholding effect, right? That you have to be traveling at a certain momenta to even start. And then you also see there's a breakdown where eventually you get to high enough momentum that everything is kind of collapsed on itself and you can't distinguish one particle from another anymore. So this has useful applications in certain regimes. So one application here, we're going to go back to Super Kamiokande, right, is that you have this large tank of water in which the neutrinos are interacting. So when the neutrino interacts in the water, it produces these muons and electrons that come out of the interaction, and they're going to produce Cherenkov light. So if you've constructed photomultiplier tubes around your detector, you'll see that light, and it's going to look like these cones here, these rings showing up on these photomultiplier tubes. That tells you the energy that was deposited. That's giving you timing information that you can use to reconstruct where would this cone have originated from, right? At what point in my detector did this particle come from to produce this ring? And you also see that for this up top, I'm showing you the image for a muon in Super Kamiokande, and you have this very clear, crisp ring-like structure. And if you look at the electron, it's a much fuzzier ring that you're seeing. And so you can take advantage of that to distinguish seeing an electron from a muon. The reason for the difference, comes from the mass, right? The muon is a much more massive particle, and so inside Super Kamiokande, the muon is going to travel with much less deflection in its path, and so it's going to produce this stable ring, right? The electron is going to bounce around a little more. It's going to be knocked around as it interacts, and so that kind of fuzzes out the ring, right? If the particle's wiggling, then that light that you're seeing is kind of wiggling around. We can put some of the concepts we've learned about together, in another way, right? So this is a liquid argon time projection chamber. This is being used a lot at Fermilab. I'm sure you'll hear about it in other talks. And so you have this very large tank of liquid argon. So a particle is passing through it. It interacts, produces other charged particles. So as they travel through the liquid argon, they're going to ionize the argon. We've applied an electric field, and so that ionization is going to drift to one side of the detector, where we have a series of very fine wire mesh channels that are collecting that electric charge. We construct that mesh in different directions, and so you see that you then get this image in 2 dimensions of the tracks of the particles then depositing charge on this plane. Now, when the particle passes through the argon, in addition to producing ionization, it's also producing scintillation. So if we collect the light, which we're going to see first, you then know the time of that interaction. And so then you can then reconstruct the 3rd dimension of where did the particles come from inside the detector to then drift. And so that's why it's called the time projection chamber, is where the name comes from. Right, so there's a lot of nice properties about this, right? Argon is a noble element. So the argon itself isn't going to have much interaction with the ions that you're producing. So you're not going to have to worry as much about reabsorption of the ions as they're drifting. It's nice that we get the scintillation light and the ionization. It's a relatively inexpensive material to produce a lot of, because in neutrino applications, we want a very large volume. It's also a reasonably high density, and so gives us more interactions. And so this is a way that we kind of rolled up all in one. We get our tracking, we get our calorimetry, we can identify our particles from these images in this type of detector. So here's one picture of the inside of a liquid argon time projection chamber. This is microboon, which is a neutrino experiment that was operating here at Fermilab. You see that beam was coming in this direction. A neutrino must have interacted here. You see this interaction point, and then coming out of it is a series of tracks, and also a series of showering particles. In the background, there's cosmic rays that are also coming from the atmosphere. So then we can put some of these concepts all together inside an experiment. So I'm going to come back first to the collider example, right? So we're steering beams of particles into each other. So they're going to collide in the center of the detectors, radiate outward. We're getting a very high multiplicity of interactions. So we want to build a large and massive detector to fully contain our interactions. And we need fine granularity, fast technologies that are radiation hard in the center, where we have lots of different interactions. So this is what the CMS detector looks like to do that. So at its very center, you have the beam pipe, which is the interaction point. And then this first layer of detector coming out is the silicon trackers to pick up the interactions coming right from the collision point, where you see there's 124 million channels in these inner layers of the detector to separate things. And then wrapped around that is the electromagnetic calorimeter here in blue. And then you have your hadronic calorimeter around that. They've put the whole thing inside a magnet, so you have your magnetic field generation to get that type of detector. And then wrapped all the way around at the end is these muon chambers then to range out the muons. And so you see as different particles are passing through it, that you might have something like a photon that isn't leaving anything in these tracking layers. And then you see this deposit of energy in the electromagnetic calorimeter. You have an electron that was leaving tracks and then again gets ranged out here. There's some hadrons that you're picking up in the hadronic calorimeter, muons passing through some of the muon layers. And so now when we come back to this image that we saw at the beginning, you see all these different tracks that are being picked up in orange from our collision point. and we see these two green towers as energy deposited in our electromagnetic calorimeter that's not associated with the track that came from the inner layers. And so this is that two photon signature that we were talking about inside CMS looking for the Higgs boson. You can also then look at neutrino experiments. As I said, the interactions in neutrinos are quite rare, right? They're very weakly interacting. They have almost zero mass, and so you want to build a detector that's as large as you possibly can with a very large target mass. You're making a very intense source of neutrinos here at Fermilab and trying to run this experiment for quite a long period of time with low backgrounds in order to try to efficiently reconstruct your particles. So again, one example of this is Dune, right, where we're building this very large set of detectors that I think you'll hear more about in other talks at South Dakota. This is one of the prototypes, and so this is a picture of the inside of Proto-Dune, which was running at CERN in a test beam. You see this is quite a large volume. On one side, so all of this would be filled with liquid argon. On one side here, you see kind of this gold mesh, and so this is the wire planes that are collecting the ionization, and you can kind of see behind them then these whitish bars that are running along. Those are the light collection devices to pick up on the scintillation light. So with that, I think I'm wrapping up here. I think you kind of got a whirlwind tour of many different technologies for identifying particles. I want to stress that doing these experiments is all about optimizing the detector design to satisfy the physics goals of your experiment, right? There's really no one right or wrong way to build these detectors. It all depends on what you're trying to do. There's a lot of tools to do that, and it takes a lot of people and effort, not just PhD physicists, to go about building and designing and then constructing these types of experiments.
Give Evan a hand. Can everybody hear me on Zoom? Say yes or no in the chat.
Yes.
Okay, great. Fantastic. All right. So we have a special question and answer or panel series for you. We got some physicists and engineers and scientists to hang out and answer the questions you have about what it's like to be a physicist. And I was a high school student. I said I wanted to be a scientist, but I did not know what scientists did. Not until I became a college student that I really understood what scientists did, and I was like, oh, this is awesome. So you guys are getting sort of a sneak peek in what life is like. We have 4 panelists for you. Some of them you might already know. Most of them you don't. So let's, who wants to go first with introducing themselves? You got to turn on. There you go.
So my name is Joshua Barrow. I'm a postdoctoral fellow at University of Minnesota working here. Person who does research in neutrino physics as well as what's called rare processes. Currently, you heard Nova earlier, I think. I'm currently Nova run coordinator, so sure that the experiment runs smoothly. On me on my phone over there, that's because the experiment is not running smoothly right now. And then I work on Dune as well, as Evan mentioned.
I guess it gets you further in the spotlight. My bad, y'all.
Sorry. All right. Not in the shadows anymore. Okay, so I'm Carrie Badgley. I'm a scientist here at Fermilab. I work in what's called the Applied Physics and Superconducting, which is way too long of a name. It used to just be called Technical. What we do over there, or what I do, is work on magnets, so magnet design, magnet testing, build magnets, so superconducting magnets and normal conducting magnets. A huge part of the accelerator. So yeah, so I get to be both hands-on and do computer simulations and testing. Or if I was just behind the computer all day, so I get to run out on the floor and climb up on the
things and test things and have a lot of fun.
Hi again, everyone. I'm Cindy Joe. You've heard me introduce myself, so I'm not sure I have to go that much more into it. But just as a reminder, again, I'm an engineering physicist. I work on sort of like these guys said, the sort of operational support side, making sure the experiments run smoothly. For instance, Josh and I work very closely together because he's the run coordinator of NOVA and I'm their experiment liaison, and I give them lots of information that NOVA, the experiment, would like to know about, for instance, how the accelerators are doing, or the facility is going to have a power outage, things like that. Thinking about this when Brian was talking about how he didn't know what scientists did when he was in high school. He wanted to be one anyway. I also, there was a career day in like 8th grade, and I dressed up. Yeah, we had to dress up as you wanted to be. I dressed up as a scientist. I didn't really know what that was, so I borrowed a lab coat from someone, and I carried around a clipboard. So I will say that I do neither of these things in my everyday life, so I wasn't quite there, but I did end up as a scientist, so that was pretty cool.
I'm Evan Niner. I'm an application physicist here at Fermilab. I work in the particle physics. So as kind of touched on my talk, I started physics. I did the NOVA experiment for my thesis. Then I came to the lab and did a postdoc, again, mostly working in neutrino physics, NOVA, and both Dune. Then I moved over into helping manage operations at the test beam facility and the irradiation facility that I talked about earlier in my talk, right? So, a lot of my day-to-day is, test beams can be quite stressful for the users, right? They're coming with their prototype detector for just a week. They have to interface with Fermilab, get it working, get some data out, and then leave for the next experiment. So there's a lot that we do in terms of, scheduling the experiments, working with them to make sure they're prepared, have all their trainings, can get badged and on site, can get their experiment safety inspected, and then help them, work over the course of their weeks while they're here to make sure their experiment is out of it, connecting them with the lab resources.
All right, so these are your 4 folks who are here to answer questions. Oh, we got one already. So what we're going to try to do is do one in person and then one also in Zoom. So if you have any questions, the chat is up on the screen, type it in, and we'll get to the questions in order.
Okay, this is general, but like, what does a day in the life of a physicist look like?
Who wants to take that one?
Start here at, so my day, there's often a lot of meetings that are involved on different things, that can sometimes or most of the day, depending on the day and the person. And then, at test beam facility, a lot of my day is then, when we're running beam, so the 8 or 9 months of the year that we're typically operating beam, a lot of my day is, walking around the facility, helping users, with their experiments, right? Making sure, if they need parts or tools or things, answering questions, kind of coordinating that. So I like, part of the reason I ended up working at the test beam is I like the variety that comes there, right? And that we're getting, dozens of experiments over the course of the year. Everybody's doing something different, right? There's collider physics, there's neutrino physics, astrophysics. So you get to learn a lot about these different things that are coming to interact with a lot of people. I still do some NOVA work on the side as well. So some of my day can occasionally be at more research things, writing code, that type of thing.
So I think I'm the youngest person here.
Yes, that's
Well,
probably
other than all of you, yeah, sorry, up here on the chopping block. So I came to Fermilab in 2019 as a graduate student at the age of 25, I think. So, which is scary to think that I've been here for that long. But on a day-to-day, when you're doing work on an experiment, generally you're doing what we call analysis. You're trying to make measurements. You're trying to better understand. A lot of that is actually just day-to-day coding, trying to look at inputs from your detector and extrapolate outputs to understand what particles are coming through. And that is a highly complex problem, generally, years to develop. So I graduated after 5.5 years of doing that in some way. Got a postdoc postdoc before working on, and when I came here under MIT and University doing the acquisition, research, and development, the day-to-day of that was a lot of plugging in wires and putting up computers and trying to get things out of. Of course, nothing worked after 2.5 months doing it. So a lot of it is problem solving very quickly. Now in my new position, I'm not doing physics that much. Sorry. Basically doing operations where now I'm in charge of Evan coming to his shift on Monday, and putting out fires where, like, the fire detector right now at Nova, which is 100 kilometers away, is not working properly. So organizing people to work on that, and then we're talking about doing a refurbishment of the near detector, which is underground here, 100 meters underground, and getting all the people together to do that, and all those people and their tools and things like that. So it's a much different kind of graduated change where you do get your hands dirty sometimes, especially when you're young and spry. And as you get older, it kind of changes. To be clear, I'm only 30, but I look 40.
All right, so I'll try to be quick, but I would say that there is no average day, week, month. Like every single day I'm at work is very different. A lot of it's putting out so if you're on an experiment, I'm on a lot of experiments. I'm on mu-to-E, PIP2, G-2, and then I'm also the head of the test. So it's kind of like whatever's broken that day is what you go work on. But on top of that, you are doing research and you are working on, and then on top of that, you're presenting research at different conferences in the world, or in collaboration meetings for these different governments, and they could be all over the world as well. So traveling to visit vendors who are building things for us, making sure that they're doing things correctly. So a week, I'm in a different town. But I have a lot, and that's what I think Evan said. It changes all the time, and that's what.
Yeah, I've had 2 different roles in my time at Fermilab. I started out as an accelerator operator in the main control room, as I mentioned earlier, and an accelerator operator, you're basically tasked with monitoring, controlling, and fixing all of the accelerators on site, and you're doing that in shifts around the clock. I mentioned, for instance, talking about this in my physics slam presentation. You guys can look at that. It's from like 2015, so it's a little outdated, but the life of an accelerator operator is still pretty much the same. But when I was an operator, I did spend a lot more time both in the field, on hands-on on machines, and sometimes literally like miles away from the control room. You drive out to some far part of site and take care of a thing that's out there. And sometimes you're in the control room all night, working on a problem from behind a computer. It really depends on what's going on. And I think that that's an aspect of science that we don't fully appreciate when we're not in it, is what you do is what needs to be done. So experiments, for instance, operate at many different phases. So now that I work much more on the experiment side, there's experiments that are sort of in the planning and construction and commissioning phase, where you've planned this thing out and now you're building it and putting it together, and that's a special phase. And there's the ones where they're operating, and they're trying to take data and keep running, like Josh mentioned, where you're solving the problems that have to do with running. And then there's the ones that are starting to decommission, and you're trying to squeeze every drop of physics out of that. But then also like sort of take it down in a way that that is useful to physics and the facility and all of that. So I get to be involved with all life phases of experiments at this point, and like the others, I spend a lot of my day in meetings because, as I was telling one of you, communications is a huge part of what we do, maybe even the majority of what we do. And that's not a bad thing. I mean, that's how it works, right? None of us is doing this by ourselves. We're doing it as a team, as part of
a whole. Each of our roles is, and the roles of people who aren't here, and the roles of people in the audience are important. And it's just kind of like finding your place within the larger whole and pushing that greater mission forward.
So there is another question on Zoom. I guess I can come in and answer it, but there's also something in the audience. So the next question on Zoom was basically what sorts of education and things do you need to get here? And we're going to have a whole session on that next week. Maybe we will skip this so that we can go into more detail next week, Maria. And then in lieu of that, we will take another question in the audience. But we do want to see more stuff on Zoom, so please keep going.
So speaking of decommissioned, projects, is there any plans to do something with the Tevatron?
Yes, I keep this one. Yes, so when I started at the lab in 2010, we were still running the Tevatron. We did for another year or more after. It took its last beam in 2011. So the Tevatron, just to explain, was Fermilab's flagship accelerator for over 25 years, and it was the highest energy accelerator in the world for most of that time. It's a proud part of our history. It was a proud part of a lot of amazing discoveries that are part of that are just discoveries in particle physics, the top quark, the bottom quark. Parts of the Standard Model and other major discoveries were made using the Tevatron. So it's a special machine. That being said, as accelerators age and as technologies develop, again, it's all a trade-off, right? You're trading off resources that it takes to maintain something, what you plan to get out of it, what funding you have. Sometimes there's challenges such as literally, this part is not made by a company anymore and we can't get any more of them, so we can't fix whatever. Sometimes that happens, right? So you're trading off the resources of what you can get out of it versus what you need to put into it. And I think at this phase, the Tevatron, I don't think there are plans to, for instance, start it up again and start colliding protons and antiprotons. But, quite a lot of it has been too decommissioned for that. I have sometimes heard people talk about ways to use the space. And I have and also I should mention certain parts of the tunnel are still used for other things, not the Tevatron parts per se, but parts of, for instance, the switch shard, which goes out to Evan's test beam, goes through the same tunnel and shares some of the similar. And this does happen often where I don't know if any of us know an experiment that ran exactly the time it was. I think they tend to all you keep coming up with ways to use them or recycle them. That's quite common as well. Again, just to try to squeeze every drop of physics out of the time and effort and money.
Anybody else want to take a stab at that?
So, as far as I know, there is a plan, but it's not official in any way, to recycle some of the parts of the Tevatron. I have to go closer.
Yeah.
Oh my gosh, I don't like the sound of my voice. So the muon collider is a plan that has been around forever. If you've ever heard of the Large Electron Positron Collider, LEP, is that right?
Mm-hmm.
Basically doing electron-positron collisions, but with muons and anti-muons. And in principle, you get some better physics out of that at radiation. In principle, you can push more down your beam. A lot of problems that they're trying to solve right now, but there are always, as Cindy said, things that people want to reuse. Works on with a lot of people is a 2x2 argon cube demonstrator for the near detector for Doom. And done is that they've recycled an old detector set of parts for a front-end part and a back-end part. So basically, if you have a particle come through and it goes through your argon, you can track it at the front of it and the back of it with other kinds of detectors. Those are really old, but they work. And some of the same components that go into that detector, I was in Israel, and they did it for muon tomography. They do actually archaeology using these same detector components. So one thing that you always learn here is how to recycle.
Okay. So we got a question from Zoom. Do you prefer computer simulated work or hands-on work? Let's take that one.
Personally, I like, a bit of both. I think for me, sitting there writing code for a year and doing nothing else gets boring. But those are fun types of problems to engage in, and the same of, doing hands-on. It's to have variety. It's nice to.
I would also say both. I would get bored doing.
Disagree, but I did most of my PhD with simulation. So I love how to model things and making code pretty, even though that all physics code is terrible. And anyway, I connect on a level with people who do analysis and do kinds of modeling simulation a little bit more in some ways. I've learned now is operations that, and do the other thing too. And it is fun, but I do.
All right, what else we got in the audience?
This is more of a general question, but what would you say about like the stereotypes between like the work and life balance? I mean, like ideas kind of portrayed scientists as like these people who just like work day and night, like no breaks.
Okay, so I have a controversial opinion about this. When I was in graduate school, the same question was asked by a prospective graduate student coming into, and people are obviously concerned about this and should be. The thing that I say with respect to this is that the amount of opportunity that we have, that our country and the international community have given us the ability to do this kind of work, that a lot of us find incredible passion in. If you're not willing to work a lot for that, whatever that number is, and opportunity wasted in some respect. So for some people, that's 30 to 40 hours a week. For others, it's 30 to 50 or more. And I know that Cindy and other people in operations sacrifice a lot more than that sometimes. But this is an incredible place. You're around incredible people. And a lot of the times you don't even notice that that time it does become a family in some respect. One wonderful thing that I've gotten to experience here at Fermilab is a wonderful culture. And when you have that culture that, in my experience, is a little bit better than some of the other national labs, it doesn't feel like you're trained in the same way.
I can speak up this. Go ahead. Go ahead, Cindy.
Yeah, I think I want to agree with that. I also want to push back against it a little bit, and not in a anti-Josh way, just in a different perspective. I think that everything that he said is true, and I want to add on to that by saying that I think that this is and should be a part of a greater life, and how much of that life is up to you, that you should find what works for you. And there have been times in my career when this really was a lifestyle. For instance, when I was an accelerator operator, that's a lifestyle. You're working in rotating shift schedule in which you're coming in at night and weekends and days, and it's kind of the whole life has to all fit together. But there are also times when this has been a smaller part of my life, and that's also okay. And so I think sometimes the fear of work-life balance can scare people off. And it doesn't, that's what I want to say is it doesn't have to be that way, that you can find the balance that works for you, but that you should be paying attention to the balance that works for you. So you should watch for signs of when that isn't working out. You should watch for signs of how it affects your life. Like, for instance, relationships is a big thing. And I mean all kinds of relationships. Many people come here internationally. They're leaving their families, they're leaving their friends, they're leaving stuff behind for some period of time because that's a dream that they're chasing, and they find that worth it to them. But then there are other times in life when they might not find it worth it to them, and people have to make a different call or a different balance. And so I think it's important to kind of listen to yourself and your priorities, and those priorities can shift over time. But that I would urge like somebody who's kind of looking into it and being like, do I want to take this on, to try to pay attention to what's important for them and try to find a situation that works for them. So for instance, graduate schools, there are some schools and teachers and situations where more will be, I don't even want to say more, different will be demanded of you. And there are other ones that are a little bit, I guess it doesn't have to be, like, I think when you think about it as a sacrifice, it's things up, but it can also be you're gaining something, right? So you are prioritizing the things that's so important to you for a period, and then your priorities change, you prioritize them. So it doesn't have to be, oh, what drudgery, oh, I hate this. It can be, oh, I love this, and I'm getting what I wanted. But you shouldn't let other people tell you what you want. You should figure out what you want and pursue that. And I do think that it can be done with greater balance than not. So Evan, for instance, has kids, and you know, many of us have just had.
So when I started graduate school, I had two small children and I was a single mom, and so I went through graduate school with two small kids, and I think that the flexibility of graduate school actually was better than if I had some 9-to-5 job somewhere else, because I was able to pick up the kids from daycare early, actually hang out with them during the day, put them to sleep, and then do homework. So it kind of just like broke up when I was working, but I think for me it actually helped work-life balance. And I think I still have a lot of that flexibility now as a scientist. If I really need to leave at 3 to do something, I can. Whereas if I worked at so although I do end up probably putting in more than an average week, I also have that flexibility in there, which I really appreciate.
So I think all three of them, I want to chime in here. I think all three of them said things that are all do kind of relate to each other. Work-life balance is an issue and it can be a problem, but I think people who choose this lifestyle self-select in such a way that they enjoy this effort. So, I mean, I work many hours. I also have a lot of opportunities. I'm also very happy with my life. I wake up every day and so
I'll add, because Brian knows some experience in the last year, had a lot of change. What I would say is that as long as you are motivated to work on what you're working on, and you're surrounded by good people who have the best intent for you, that's really the key. So if you ever go graduate school beyond things like graduate, something, really want to be working for people who have the best intentions for you, professional development and your personal. Not everyone sadly does that. Not a physics problem, that's an everybody problem, but can ensure that.
okay. So I see the next question is from Layla. And Layla, you're asking about college majors, but again, this is something that we will go into detail with next week. We're going to skip that question. I'm sorry to do it, but we're going to have a long conversation about how one becomes a physicist. Okay, we got another question in the audience. Got two. Who was first?
I guess my question, this might be a bit cliche, but do you see AI being integrated into what you do within like maybe the next 10, 15 years? Because, I mean, obviously, like, it's become a lot of other industries and even within things like computer science. So do you see it becoming part of what you do as well?
Yeah, I mean, it's already in a lot of ways heavily integrated into experiments, right? In, various ways, but a lot of, when you're writing algorithms to correct what happened inside your detectors, right? So you have these tracks of particles and things that we talked about, and how do you figure out what those were and identify them, and you build these algorithms. There's a lot of, machine learning, artificial intelligence in various applications that's at a lot of applications even on the accelerator side to to detect, how efficiently am I running my accelerator, right? I'm circulating beam, and I'm noticing that losing some beam in one spot, right? And where did that come from? Did a magnet fail, or does something need to be tweaked? And people are writing algorithms to basically learn, have a machine kind of automatically, adjust and tune that, right? And optimize the efficiency of the accelerator, report those losses, fixes, and by some type of AI. And everywhere in our field, just like it's or in all fields, and only develop and grow, I think with
I've got something to say on it, unless you do. Okay. So AI is a tool like anything else. I've in fact been using AI for a very long time. I'd say at least a decade or two at this point. I think the first major package TVMA was in Root, which is our standard analysis package, back in like early 2000s. So the thing about being a physicist, though, is that it more or less teaches you how to solve problems. It backdoors you into being a very good problem solver by asking you to solve the most difficult problems in the universe. What you learn is that AI is one of these tools, and once you effectively deploy this tool, that's where the use is. Right? So I guess I'm going through all that to say that I think physicists is one of the few jobs where I think it'll take a long time for AI to replace us.
Very small addition also to remind you that there are physical aspects to our jobs which are difficult to outsource in that way, right? So you also need people to climb on the magnets and put them physically together and things like that in a way which, for instance, over the pandemic, quite a lot of people were working from home, but quite a lot of people could not work from home and needed to come in to keep the place running. That was seen as like this necessary thing to take care of the facilities and the infrastructure, and that you still need people for that.
Add one thing. GPT, everyone uses it now. I think pretty much every scientist here, if they do any aspect of coding, has utilized this. They helped a colleague write a interface for DAQ, for data acquisition, I should say. And we were looking at manuals and we couldn't understand. And then I think there's definitely aspects of AI that are going to be helping us, but not necessarily replacing us. And if you can integrate, as Evan said, workflows that people use for image processing, things like this, in physics, you're going to become really closer to understanding
All right, we got something from Zoom. Do wormholes have any connections with black holes?
So this is EPR equals ER, I
Yeah.
think. Einstein-Rosen bridge equals, Rosen? I can't remember. It's a thought that people have theoretically, not substantiated by any data.
So we just got our first picture of a black hole like a few years ago. They are ideas that exist. It's not quite clear what we can say about them in any definitive manner. All right, what do we have in the audience?
So you talked about a lot of coding. Which languages do you like prioritize in your daily life?
C++, C++, C++.
Don't listen to him. Don't listen to him.
Python is terrible.
Don't listen to him. Don't listen to
For
him.
GUIs, it's great. For text editing, sure.
Say it depends a lot on the applications, right? I mean, personally,
Listen to him. That's the right answer. What? That's the right answer.
A lot of experiments have been around for a long time, right? Fermilab is more than 50 years old, as is CERN, and so you might find yourself needing to write Fortran or other very old languages because that's what the software 50 years ago that is still running is using, because if it's still working, it's gonna keep, we're gonna keep using what works probably before we replace it with something else. And so you might find yourself encountering a lot of different applications and a lot of these legacy applications that you're either then having to learn or you're having to port them to a more modern language, right? But then you still have to figure out how it worked in whatever old language was being used so you can adapt it to a newer language. So I think the most important skill as a young person isn't saying, well, I'm going to learn Python and that's all I'm going to use, right? It's understanding how coding works at a more abstract level, understanding kind of the, all languages, you can kind of do the same fundamental things in them. It's just different syntax, right? So if you teach yourself how to learn a language, it's just like speaking languages, right? If you know the process that you go through of how do I learn a language, then you have that flexibility to adapt and pick up whatever tool you encounter, because you'll encounter different ones.
Therefore, the best to learn from, but okay.
I want to comment on this one. So I've done assembly, Fortran, C++, yes. I've done IDL, I've done Python, and MATLAB has its own weird thingy language, and then R and Octave and Mathematica. True thing you need is flexibility, as Evan said. Different languages have different strengths. Want to pair the strength to the problem. But yes, you should learn C++ because it teaches you how to properly program object-oriented languages. Don't let that be the only thing you do. Another one, wait, we got to get one off the Zoom. Oh. Oh, there you go. Hey. That one. Yeah, I don't think we have another one yet on Zoom, so let's go to somebody in the audience.
Does Fermilab exclusively work with other national laboratories, or do you interact with the private sector? And if so, how do you do that?
I mean, we work with universities, other labs, international labs, but we also have full partnerships with industry. Building that was specifically built actually for that, the Illinois Accelerator Research Center or something. I don't know actually. So so that was built to partner with industry, and so there's stuff going on in that building that allows industry to come in and use some of our tools and expertise to help in our working with industry and quantum.
So that is a very good question, because here's what a lot of people don't know about national laboratories. We have what's known as an Office of Partnerships and Technology Transfer. The reason we have that office is because literally what we do, again, let me back up a bit. So I think I said this in the first lecture or the second lecture, that we were started as like an offshoot of the Manhattan Project, right? The U.S. government was like, oh man, we really need to know a lot about nuclear physics. So the Manhattan Project works pretty well. So let's just copy that model and turn those into national laboratories, right? Turns out that a lot of the scientific innovation that you think are attributed to private companies actually come from national laboratories. We use an iPhone, that touchpad. Apple didn't invent that. They patented it, but they didn't invent it. It was invented by a university in conjunction with a national laboratory. A lot of the things that you think were produced by some company that claims they built it, typically built either in a university or in a national laboratory. So our integration with private enterprise is very deep, and it's so deep that most people don't know how deep it is. I would not be surprised if almost half the things in your electronics that you use, almost half the technology you use every day was probably developed either at a university or in a national laboratory. Yeah, a lot of it was Bell Labs, which is sort of like this old, well, it was private, but it was a national lab sort of thing. Regardless, the integration is very deep. You will find a lot of things. If you dig deep enough, you'll find the patents and the original ideas come back to these sorts of locations.
Like, part of the reason behind that, right, is, I mean, part of what national labs allow us to do is pursue that kind of research that doesn't necessarily, at the time that you do it, it's about pushing the boundaries or doing what you need to do for this very specialized thing, such as like, I need a detector that sees these particles that we don't know exist yet. Or, you know, I need to run this machine that goes to energies nobody has ever achieved before. And in developing those technologies, sometimes those then eventually spin off into things that an industry is interested in, turning into money, but we didn't do it for that reason in the first place. And that's where the innovation came from, doing things that didn't necessarily have monetary value from the start. So, I mean, the canonical example that a lot of us use to add on to Brian's example is of the World Wide Web, right? Back in the day, and Berners-Lee and CERN and these other people were like, we have huge amounts of information coming from our detectors that we'd like to move from one site to another site. How do we do that? Let's come up with a protocol and a means of doing that. At that time, nobody else had or needed to move huge amounts of information from one site to another site. It wasn't, you know, people were like mailing around pieces of, and when we developed this protocol and started moving this information around, again, for our detectors, for our scientific purposes, eventually people were like, hey, we want to get on that train. We want to move our information around. And now, you know, you can't do without the internet. But yeah, I think that these things are very related to each other, and that we get to do where we get to use time and resources for these things which don't end up making money yet, I think is.
Yeah, so while you're passing, somebody on Zoom said the internet was a DARPA project. That is true. It was an ARPA project. It was as a part of DARPA. First transfer. And also Wi-Fi was built with another ARPA project with the. And then, yeah, somebody else is saying www with CERN. That was their implementation of it. First server ever at CERN, like out behind a glass case. So if you ever get out to Switzerland, you can. Yeah. Good.
So I just wanted to add, there is always this question that people, favorite question at family. A lot of the technology that we work on here and the experiments that we do are not applicable in today, 1,000 years from now. But there is one thing that we produce here that is happens here, and also what our connections with outside the lab are, and that's our people. Because there is.
Move the mic.
I can hear myself.
But they can't hear you.
Oh my gosh. Yeah. I'm sorry. Okay, so wow, I'm really loud. The point being though that our people are actually our product in some respect. It is here that's a training ground for people to learn how to do technology, to learn how to do analysis, coding, interfacing with people, looking and working with a bunch of different people from all around the world, and that's an indispensable product. And a lot of the people who we train here go on to, yes, be professors or scientists, but they also go in to data science. They go and they become doctors in other ways. They can do a lot of different things, and that's.
All right, so this will be the last question. Probably from the audience. We got something else from Syed asking, is dark matter disproven by James Webb? I think the answer there is no. I don't know how you would disprove dark matter, but you would need more than observations of the cosmos, I think, to do it, although it would be an important part. What else you guys got from the audience?
What led you to want to work at Fermilab? Like how, when, and why did you decide that like this is where you want it?
Okay, I'll start. I was getting my PhD down at Texas A&M, and I actually planned to go either into industry because I worked at a company up in New Hampshire called Kimball Physics that makes electronic offer to go back. But because of funding shortages in my lab at Texas A&M, I came up to Fermilab, finished what I was working on for my PhD, and I fell in love with the lab. Like a college university, kind of like industry, it's weird in between, where we still get to go to colloquium and lectures on topics outside of our field. We get to area on site. We have, all these things. So it was kind of just a neat combination that I just hadn't considered because I didn't know about it. I thought academia or industry. Were great. I liked what I was doing, and so.
Yeah, so I grew up in northeastern Indiana, and so I first came to Fermilab in high school. I was interested in going to college in physics, and so one weekend my family just drove over to Chicago. We just went to Fermilab on a Sunday, took one of the Ask the Scientist tours, just took a tour. So that was the first time that I came, and then I went to school. I did a physics degree, and then in graduate school, ended up picking a professor that worked on the NOVA experiment to do my thesis on, and so NOVA was based at Fermilab. So during graduate school, I spent a lot of time coming back and forth for days, weeks. I lived here for about 9 months in graduate school, doing my thesis research, and so during that time in graduate school, at one point, I went into grad school thinking, I probably want to maybe be a professor. And during the course of graduate school and coming to Fermilab, I decided, no, I think maybe I'd rather work at a national laboratory than at a university. And so then when I was looking for postdocs, I was like, well, I would like to try to do a postdoc position at a national lab to see better if that's really what fits. So I did a postdoc here at Fermilab, and I've been here now in some capacity as a user, as an employee for 13 years.
Graduate school and stayed.
So I guess I had an interesting story, and then we'll. So I went to graduate school at the University of Michigan. I remember when I was a graduate student, I really wanted to. Things didn't quite work out that way, so I wound up coming to Fermilab and doing my graduate work here, and really found myself enjoying life. When I graduated, I got my PhD. I was offered a chance to field of, you can think of it as nuclear physics, high energy nuclear physics, looking at neutrinos, very closely related. And I actually got offered some time at CERN. So I went out there and stayed out there for a year. I realized I didn't like it. When you go to Switzerland, and if you go and you check out CERN, I think you'll see what I saw. But really, like, as far as a place to do particle physics, Fermilab is quite nice. Beautiful. It's close to a major city. All sorts of things you can do here that you can't do anywhere else. On top of that, big draw for me is national laboratories pay very well. Pay better than most universities. Because you essentially have all the benefits of working for a military defense contractor without having to make weapons. All the benefits of working for a university. And there are some things that are not quite what you would want. So, for example, I do have to answer the DOE. So when President Trump was in office, he did say that I could not talk about climate change. I decided not to do it. So there are negatives, but the positives greatly outweigh the negatives. So with that, I think, unless you have would you like to say anything? With that, I think we'll end this session. So let's thank our speakers. And I will see you next week. Everybody on Zoom, feel free to, I saw some extra questions in the Zoom. I'll answer them right quick. But feel free to leave if you don't want to hear the answers. Oh, I'm going to give a talk on climate change. But yeah, back then, Trump literally said we had to remove all mentions of climate change from the website. That was a directive from the president's office. Yeah. So John, you asked the question: Do I think that private companies can patent and monopolize inventions were only able to be produced by taxpayer-funded research? I mean, yes, but that's sort of what we're here for. We use tax money and we more or less develop it so that private companies can have something to sell. One of the things we do, in addition to probing the nature of the universe. So with that, we're going to sign off. We'll see you guys next week.